Welcome, everyone, to today's Explainer. I'll be your chemistry professor today, guiding you through the genuinely mesmerizing science behind the classic blue bottle experiment. If you've ever been captivated by a chemical reaction that just seems like pure magic, literally changing colors right before your eyes and then changing back again, well, you are in exactly the right place. We're going to break down exactly how this happens, step by step. We'll take it from a simple visual trick all the way to understanding the complex natural patterns of the universe. So, grab your lab notebooks and let's get right into it.
Here's a quick look at the syllabus for our masterclass today. We'll start with the physical setup, dive right into the kinetics driving those color changes, and then observe some spatial patterns in an open dish. After that, we'll connect these phenomena to biology, cover proper lab disposal, and finish up with a quick pop quiz.
Section 1. The Setup. Managing Chemical Reagents.
Now, I know some of you might be hoping for the explosive, ear-defending drama of the famous barking dog demonstration. You know the one, using nitrous oxide and highly volatile carbon disulfide to create that roaring blue flame and an actual barking sound. But today's blue bottle experiment is a much safer yet equally profound visual marvel. So, no ear defenders or blast shields needed today. Instead of explosions, we're relying on a calm, contained, color-changing redox reaction using simple sugars and a dye.
All right, take notes on this step-by-step methodology. Combining these three reagents in a closed bottle sets the stage for the entire reaction. First, we create an alkaline environment by mixing a strong base, like sodium hydroxide, with a reducing sugar, which in our case is glucose. Second, we add a few drops of our star indicator, dilute methylene blue. And third, we seal the flask. But, and this is absolutely critical, we have to leave a significant amount of air in the headspace of the bottle. That trapped air isn't just empty space, it's an active, vital ingredient for our experiment.
Moving to Section 2, Kinetics and Color Changes. Let's demystify the magic.
So, the color change cycle we're observing has all the distinct features of what's called a clock reaction. It acts as an absolutely perfect illustration of pseudo-first-order kinetics. Basically, in complex chemical systems, you've got multiple subreactions happening simultaneously, all at completely different rates. A clock reaction becomes visible at the exact moment a specific limiting reagent runs out. It's literally like a chemical alarm going off.
Let's look at this quote. The reaction is first order in glucose, methylene blue, and hydroxide ion, and zero order in oxygen. Well, what does that actually mean? It means when the bottle is just resting there, the underlying kinetics take over. The alkaline glucose solution is working hard to reduce our blue dye into a completely colorless state known as leucomethylene blue. And because the reaction is zero order in oxygen during this resting phase, the dissolved oxygen is gradually being consumed. Once that oxygen is totally exhausted, the glucose reduction proceeds unopposed, and boom, the liquid rapidly turns crystal clear.
Okay, so the absolute crucial point here is that vigorously shaking the bottle dissolves that headspace oxygen back into the liquid. This fresh rush of oxygen acts instantly. It rapidly reoxidizes the leucomethylene blue and brings back that striking, vivid blue color. As the flask rests again, the cycle just starts over. The oxygen depletes and the color fades. You can actually repeat this shaking cycle over and over until either the glucose or the oxygen in the headspace is entirely used up.
Section 3. Patterns in Petri dishes. Taking chemistry out of the bottle.
Let's see what happens when we alter the boundary conditions by pouring our solution out of the bottle and into a dish that's totally open to the atmosphere. Exposed to the open air, a really fascinating new phenomenon takes over. Rather than just a uniform color change, we start to see incredible spatial structures. We're talking mosaic patterns, intricate web-like structures, dynamic spirals, and branching lines connecting to one another. Why does this happen? Well, molecular transport through diffusion is now physically fighting with chemical kinetics. Oxygen is constantly exchanging right across that air-liquid interface, creating what we call chemically driven convective instability. It is essentially microscopic weather happening right there in the dish.
A quick pro tip for those of you recreating this in the lab: remember that temperature plays a fundamental role here. Dropping the temperature actually yields a much clearer, less homogeneous spatial phenomenon. If it's too hot, the kinetic energy causes everything to mix way too rapidly, blurring all those distinct lines. Cold water slows the diffusion down just enough to let these breathtaking, high-contrast chemical waves develop and sustain themselves.
Section 4. Nature's reaction-diffusion. Let's take this from the lab to biology.
Now, let's step out of the laboratory for a second and see how the fundamental blueprint we just created governs the macroscopic world around us. The dynamic interplay of reaction and diffusion we just witnessed is the exact same mechanism that paints the striking black and white stripes on a zebra or even the intricate bands on a marine angelfish. Biologists and mathematicians call these Turing patterns, named after Alan Turing, of course. It's a spontaneous symmetry-breaking process where an activator and a faster diffusing inhibitor basically compete, locking into static, repetitive biological designs. So our little blue bottle is really just a fast, liquid version of a zebra's coat. How cool is that?
Section 5. Safe neutralization. Proper laboratory disposal. Before we wrap up our benchwork, we really must address professional cleanup and waste management. As you know, you never simply dump active, caustic chemistry straight down the sink. Because our initial mixture utilizes a strong caustic base like sodium hydroxide, it is absolutely imperative that we carefully neutralize the pH level to a safe, neutral 7 before disposal. Our solution might be sitting at a highly corrosive pH of 13. So, by carefully introducing an acid to lower the pH and then using standard baking soda, just sodium bicarbonate, to gently buffer it back up to a perfect 7, we render the waste completely non-corrosive and totally safe for standard laboratory disposal. Remember, safety and responsibility are the true marks of a great chemist.
All right, Section 6, Professor's Pop Quiz. Let's test your knowledge.
Okay, class, put those notes away. Let's see how much of this masterclass has successfully diffused into your brains. Question 1. In our closed bottle setup, what specifically causes the colorless solution to instantly turn blue again when we shake it? Think back to our discussion on limiting reagents and physical actions. What are we physically forcing into that liquid?
If you guessed oxygen, you are absolutely correct. The oxygen trapped in the headspace acts as the vital catalyst for oxidation. The physical agitation of shaking the bottle dissolves it right into the alkaline glucose mixture, ripping electrons away from the leucomethylene blue and restoring its vibrant color, at least until the oxygen is entirely consumed once again.
All right, question 2. Moving to the open dish, what two mechanisms drive the dynamic spiral and mosaic patterns when the solution is poured out and exposed to the atmosphere? Consider what's happening right at that boundary where the liquid meets the air.
You nailed it if you remembered molecular transport through diffusion and chemical kinetics. The physical spread of the molecules fighting against the speed of the chemical reaction creates those absolutely stunning visible structures. Which leaves us with a final, provocative thought to ponder long after class is dismissed today. If a simple mix of sugar, dye, and air can self-organize into such intricate, lifelike patterns, what other hidden clocks and canvases in the universe are just waiting for us to uncover their underlying chemistry? Thanks for joining today's Explainer class. Keep questioning, keep experimenting, and I will see you in the next one.